Hey guys, I'm Ammar Abed.
And I'm Peeples.
And this is our pre-cal extra credit project.
So today we'll be talking about radians.
So what are radians?
Well, radian describes the plane angle subtended by a circular arc as the length of the arc divided by the radius of the arc. 1 radian is the angle subtended at the center of a circle by an arc that is equal in length to the radius of the circle.
What?
I don't know either. So here's a simpler definition. A radian is a unit of measurement based on a circle that is used across math to measure arc lengths, periods, angular speed, and more. Let's demonstrate what a radian is using a pizza.
So radians are based off of pi. Wait, no, not that pi. This pi. In fact, every circle has a circumference of 2 pi radians.
Let's look at this pizza. If I cut down the middle, I've drawn the radius of a circle. I've also drawn 1 radian. This means that an arc with the length of 1 radian is equal to the radius of the circle. In fact, if this pizza was 4 inches across instead, we would still have a circumference of 2 pi radians, because radians are proportional and not a set value.
But we're all used to degrees, so how are we supposed to convert them to radians? Well, to convert from degrees to radians, multiply the degrees by pi and divide by 180. To convert back, multiply the radians by 180 and divide by pi. This works because a full circle of 360 degrees is 2 pi radians, so 180 degrees is pi radians. Also, 1 radian is equal to 57.296 degrees. Well, in our next few videos, we're going to start using radians to demonstrate how to draw trigonometric functions. See you next time and have a fantastic day.
Hey guys, we're back for another video on sine and cosine functions.
So what do sine and cosine functions look like? Well, not that sine. Not that sine either. That's a sine function.
So, a sine and cosine function are what are known as sine waves. The graph oscillates from right to left within a certain range.
So let's graph a sine function.
The function we're looking at is 2 sine 4x plus 2 pi plus 1. Let's make this easier by breaking it up.
So first, we'll look at the a, or amplitude, which in this case is 2. This means that the wave will only extend to 2 units above and below the midline.
Next, let's look at the b value, which in this case is 4. This value lets us determine the period of the function, which is how long the wave will go before repeating itself, or basically one full cycle of the wave. The period is found by inputting the b variable into 2 pi over the absolute value of b. In this case, we get pi over 2.
Now let's look at the h value, or the phase shift. Remember, we need to factor out the b value, or 4, which leaves us with negative pi over 2. The formula for h is x minus h, so since our equation is x plus pi over 2, the phase shift is negative pi over 2. This means that our equation will be shifted pi over 2 units to the left.
Finally, we need to look at the k value, or the vertical shift. In this case, it's 1. This means that the midline of the equation is y equals 1 instead of y equals 0. This also means that amplification will shift up, so now the wave will extend to y equals negative 1 and y equals 3, instead of the normal y equals negative 2 and y equals 2.
Remember that because it is a sine function, it will normally pass through the origin, or 0, 0, while the cosine function will pass through the point 0, 1. The sine and cosine functions are identical, except for a phase shift of pi over 2 between the two of them.
And that's it for sine and cosine functions.
Have a fantastic day.
Hey guys, we're back for another video on cotangent and tangent functions.
So what are tangent and cotangent functions like? Well, we need to think of what a tangent is first. Oh, this reminds me of a time when...
No! Don't go off on a tangent. And no, that's not a tangent. That's not the tangent we mean either. That's a tangent graph.
An important thing to remember is that the tangent graph is based off of the cosine function, and the cotangent graph is based off of the sine function. We'll see how in a second.
So, let's draw the cotangent function 2 cotangent 4x plus 2 pi plus 1.
So the first thing we do is draw the sine function. In our last video, we talked in detail about drawing these functions, so let's do it fast.
So, to draw the sine function that will help us draw the cotangent function, just replace the cotangent in the equation with sine. This is the same equation we drew in the last video, and is represented by a midline of 1 with an amplification of 2, a phase shift of negative pi over 2, and a period of pi over 2.
Now the next thing you need to do is draw a vertical asymptote wherever y equals 1. Generally, these would be considered the zeros of the equation, but because of the vertical asymptote, y equals 1 is technically the zero line.
Now that you have drawn a vertical asymptote through every zero, begin drawing the cotangent function itself. The way to do this is to start in the upper left corner of every area between asymptotes and move down to the bottom right corner. However, the cotangent function should cross the midline at the x values of the lower and upper extrema on the sine function.
It's important to remember that the tangent and cotangent functions continue infinitely in terms of range and domain, but they have asymptotes limiting their domain. Tangent functions always increase, so they would go from the bottom left to the upper right, unless they are reflected. And the opposite for cotangent functions, as we graphed them from the upper left to the bottom right.
And that's it for tangent and cotangent functions.
Have a fantastic day.
Hey guys, we're back for another video on cosecant and secant functions.
So cosecant and secant functions are sort of the reciprocals of the sine and cosine functions. What this means is that they will turn out in opposite directions from the wave. If that made no sense, don't worry, it'll be clear once we graph the function.
Let's draw the function 2 cosecant 4x plus 2 pi plus 1.
So since cosecant is a reciprocal of sine, we'll draw a sine function first. We'll replace cosecant with a sine and graph that. This is the same graph from the last two videos. It's represented by a midline of 1, with an amplification of 2, a phase shift of pi over 2, and a period of pi over 2.
The second step, similar to the cotangent function, is to draw asymptotes at the x-intercepts of the sine function or the zeros of the midline.
The final step of this function is graphing the cosecant function by going off of the extremes. The minimum and maximum extremes of the sine function are used to show the turning points of the cosecant function, which will touch the extremes of the sine function and expand away from the x-axis, causing the cosecant function to never touch the x-axis.
Remember that the cosecant function will move towards the asymptotes on either side, but will never touch it. This causes it to never have the same x value as the x-intercepts of the sine function.
This concludes our video on cosecant functions. Thanks for watching and have a fantastic day. Hey guys, we're back for another video on angular velocity and linear speed.
So, angular velocity is a measure of how fast a fixed point will rotate on a circle in terms of radians. This means that no matter what point on the circle you use, the angular velocity will remain constant, as the radians are proportional to radii and not a fixed value.
Linear speed is different from angular velocity. While angular velocity was a measure of the speed of rotation, linear speed is a measurement of the distance traveled by a point on a circle as the circle rotates. This means that unlike angular velocity, the point on the circle does matter. This is because a point on the edge of the circle will move a larger distance with each rotation than a point closer to the center of the circle.
Let's practice. Let's assume that a toy car has wheels that are 2 inches in diameter and it has 60 revolutions a minute. How fast are the car's wheels rotating in radians per second, and how fast is the car moving in feet per hour?
To solve this problem, we will have to use a method called dimensional analysis. First, let's set up what we know. We know that the car has 60 revolutions a minute. First, we need to convert the minutes into seconds for dimensional analysis, so we'll multiply it by 1 minute over 60 seconds. It's important to note that 1 revolution refers to 1 full circle, or 2 pi radians. This means that we can multiply the value by 2 pi radians over 1 revolution. Once we multiply this out, we find that the angular velocity is 2 pi radians per second, which means that the car rotates 2 pi radians every second.
Now, to solve for linear speed, you must once again use dimensional analysis. First, we know that the angular velocity is 2 pi radians per second. Now we need to convert it to hours, so we simply multiply the value by 3,600 seconds per hour.
Now we need to convert the radians to feet. To do this, we need to remember that 1 radian is the radius. If the diameter is 2 inches, that means that the radius is 1 inch, so we'll multiply the value by 1 inch over 1 radian. Now we multiply the value by 1 foot over 12 inches.
The linear speed is 600 pi, or 1,885.714 feet per hour. This means that in 1 hour the toy car will move 1,885.714 feet.
And that's it for angular velocity and linear speed. Have a fantastic day!